everybody, this is lesson 2.1 on transforming data. Okay, say that I gave you each a slip of paper and I had you guess the width of the classroom in meters. Then I collected the slip of the paper. Now, none of us are too good at guessing in meters, so our answers have a lot of variety, which is kind of fun for the activity that we're doing with these numbers. This just gives us a generation of unique original numbers. Now, say that we plot that list of numbers. Okay, so here we go, and of course I plotted a couple wrong, so don't plot those. Okay, let's have the X's. Okay, the real answer is about 9 meters wide for the classroom, so that's right down around here. Okay, that cluster of 3 points. Wow, huh? No, okay. Graph the distribution of errors, which is observation minus the mean. Now, the distribution of errors, that's a new concept to us. When we think of an error, we think of how far off we are from the truth, okay? So that's the amount that I'm graphing now, is the amount that we were off by. So we were off by 3.9 units, by 39 units, by 1.5 too few units, okay? 15 too many, 12 too many meters in the classroom, okay? So here's now the distribution of errors. Okay, so what that means is, what I want to do is I want to try to keep these axes as similar as possible to try to truly drop down the 50, try to truly drop down the 5. And we do have to go a little into the negative now because we are taking all those observations and we're subtracting 9 from it. Okay, observation minus the mean. So technically, all these observations should just go down 9. Okay, and so there they are, down 9 units. All right. Compare the two distributions of data and the errors. Subtracting 9 from each data value shifted the graph left. Shape remained the same, meaning I have 1, 1, 1, and this little cluster here. Okay, so it's kind of really right skewed, if you will. Shape remained the same. The center, x bar, was reduced by 9. Spread, sx, remained the same. Okay, my spread didn't change. My pointer finger and my pinky are just as far apart as they were before. The min and max didn't become any further apart from each other, and all the other points didn't become any further apart from each other. Okay, I'm sorry, there it goes. So my pinky and my pointer finger didn't become any further apart or any closer together. Okay, all that I did was I shifted all the points, each and every point, down 9 units. Okay, so I took the observations and I subtracted to find my errors of how short we were or how much longer we were than the true. So now the true value is not any longer 9 meters of a classroom width. It is now 0 meters of classroom width. This actually doesn't mean width anymore. It means the amount of error. So these people who guessed 9 were all 0 units from 9, from the true mean. So they all have 0 for their error. They were right on the true mean, 9. Okay. Convert the errors to feet, multiplying by 3.28. Graph using the same scale as above, and compare the distributions in errors in feet to errors in meters. So I'm going to try to drop down 50, drop down 5, or 0 or negative 5, okay, and try to keep the rest about with equal increments going up and going down. Remember that I'm changing these from meters to feet, so I'm multiplying every value by 3.28. So this number goes all the way up here. Okay, and here's all my new data. So instead of 3.9, it's now 12.8. Instead of 39, it's 127.9. Doesn't even fit. Negative 1.5 is now negative 4.9, and so on. So I listed out all my changes in data. Okay. And then one more thing I did for each of these distributions is after I plotted them, I went through and I found some summary statistics. I found the mean and the standard deviation of the first set of data. The mean was 15, the standard deviation is 10. I went here and I found the mean and standard deviation. The mean was 6 now, which was straight up 9 units less. I subtracted 9. Okay, the standard deviation didn't change a bit. Now when I took my last set of data, my errors in feet, I found that my mean was 19.8 and my standard deviation was 34.6. One more thing to take note of is that those few students that guessed 9, that they had an error of 0 And after the multiplication, they still had an error of 0 because 0 was multiplied by 3.28 to still get 0. Okay, so it seemed like values above 0 were multiplied by 3.28 and spread further right. Values below 0 were multiplied by 3.28 and spread further left. Okay. It also asked us to compare the distributions in meters to the distribution in feet. So we would say that we see a lot more spread. All right. I do technically have the same shape, even though it's very elongated, but I didn't necessarily go from skewed to symmetric, or I didn't move from symmetric to multimodal. Okay, so my shape generally didn't change, especially if I could change the scale of the graph here and condense it more, the shape would look exactly the same. Okay? All right. Let me turn the page. What is the effect of adding or subtracting a constant from each variable? So now let's talk about generalizations. We saw that worked out step by step in a real-world context. Let's talk about generalizations then of what we'll see worked out anytime that we add or subtract a constant to each observation. The center and unusual features and location will get added and subtracted. So x bar, median, min, max, every little value, q1, q3, okay? It'll get added and subtracted too. Shape remains the same and spread remains the same. So this is referring to when we subtracted 9 from each unit and the whole distribution just moved 9 down the number line. What is the effect of multiplying or dividing each observation by a constant? The center and location got multiplied or divided, so that means all these things, okay? Get multiplied or divided. Shape remains the same. It doesn't move from like skewed right to skewed left or something like that. Spread also gets multiplied or divided. Variance is a little different because it's in squared units. Variance, remember, is standard deviation squared. For example, standard deviation of 10 inches, then the variance is 100 inches. That's just how standard deviation and variance work. So if we did this, a transformation of divide by 2 on every observation, the standard deviation would be divided by 2. It would now be 5. But the variance should be divided by 2 squared. We should work with that constant on the transformation, and we should square it as well because variance is in squared units. And the variance would be 25. Okay, let's move on to a new data set though. 10, 20, 25, 30, and 40. Say that you wanted to find the mean and standard deviation of this data set. I'm going to go over to Stat, Edit, L1, and put this data set in. 10, 20, 25, 30, 40. By the way the data set kind of sounds like 25 is right in the middle. 30 and 20 are 5 away from it, and 40 and 10 are 15 away from it. Okay, so it's a very symmetric data set. The mean is 25. Let's just check it out again. Stat, calc, one variable stats. Mean is 25, and the standard deviation is 11.18. If I convert the minimum to a z-score, I get the z-score of the minimum. Convert each value to a z-score. So I'm going to take 10, I'm going to subtract 25 from it, and I'm going to divide by the standard deviation. I can also do this in my lists. Stat, edit, L2 is to take L1 and to minus 25 from it. And then L3 is to take L2 and divide by 11.18. Okay, and there's my z-scores. 13.342, negative 1.342, negative 0.447, 0.447, and 1.342. And that makes sense because I had a very, oh, sorry, I skipped 0 there in the middle. That makes sense because I had a very symmetric distribution. So when I have a mean, and I move it to a z-score, my mean gets subtracted by the mean and divided by the standard deviation. 25 gets subtracted by 25 and divided by 11.18. 25 minus 25 is 0, divided by anything is 0. So it makes sense that the mean would have the mean of 25, if it's actually a data value, and it's actually the true mean of the group, they would have a z-score of 0, because z-scores are interpreted as how many standard deviations the value is away from the mean. So these are all standard deviation values. This is saying that just under half a standard deviation above the mean. This is saying 1.3 standard deviations above the mean for this data value and for that data value. Okay, but 25 is no standard deviations from the mean. Okay, then I plotted my regular values, 10, 20, 25, 30, and 40. And then I plotted my z-scores, negative 1.3 to 1.3, and the values in between. When we standardized the data, what operations did we perform on each value, and what happened to the original distribution? The first thing we did was we subtracted each observation from the mean. Okay? Subtracted made the center decrease, because we know that subtraction is going to take this distribution and scoot the whole thing left. And we know that when you subtract by 25 for each of these, that it'll be centered at 0, because the center value gets subtracted by 25, and 25 minus 25 is 0. And then each of these gets subtracted by 25 as well. So it goes 25 to the left, where its center was 25, its center is now going to be at 0. Okay, and when we divided, the spread decreased. The center and location each got divided by the constant, so in a way they decreased too. For the standardized data, the mean is 0, and the standard deviation is 1. What happened to the mean and the standard deviation of the original distribution? Show using the transformations of the symbols. So I'm going to show in symbol form. Each standardized unit each value went through this standardization. The value minus the mean over the standard deviation. So when we transform the mean itself or transform the standard deviation itself, we should do these things. Because means are affected by subtraction and division, then we should subtract and divide the mean to find its new standardized score. If I want to transform standard deviation alone, standard deviation isn't affected by addition or subtraction. So we won't subtract by the mean. We will just divide by standard deviation. So what I'm doing is very theoretical here. I'm just, instead of transforming every data value, I'm just discussing the transformation of these two specific, not even data values, these two specific summary statistics. If I transform a mean of a data set, I will get a 0. If I transform the standard deviation of a data set to its standardized score, I get a 1. Okay? So every data set's distribution of standardized scores will have a mean of 0 and a standard deviation of 1. And that makes sense by definition of standardized score, is that it has a mean of 0 and a standard deviation of 1, meaning that we are counting out in standard deviation units from the mean. So you're either 0 standard deviations away from the mean, or 1 or 2 or 3, or negative 1 or negative 2 or negative 3. Okay? And there's the formulas just to support that. Okay? All right. That is something that you have to be able to discuss. In 2010, taxicabs in New York City charge an initial fee of $2.50 plus $2 per mile. In equation form, the fare is equal to the $2.50 constant plus $2 for every mile, which is linear, and it's a linear transformation, and that's why it fits into this lesson. At the end of the month, a businessman collects all of his taxicab receipts and analyzes the distribution of fares. The distribution was skewed to the right with a mean of 15.45 and a standard deviation of 10.20. what are the mean and standard deviation of the lengths of his taxi cab rides in miles? So what I'm going to do is I'm going to say fare and miles, and I'm going to use that equation, and I'm going to move things around so that I can solve for miles. If I knew that the mean was $15.45, then I can use this new equation to find the mean number in miles. 6.475 is the mean number of miles, and the standard deviation used to be $10.20. I'm going to only run it through the division, not the subtraction of a constant, because standard deviation isn't affected when I do a linear transformation of addition or subtraction, because spread doesn't actually increase or decrease when I subtract an amount from every observation and find a new standard deviation of that new distribution. So the distribution of miles shouldn't have that subtraction. It should just be divided by 2. So if I take take half of it. Okay, so if I take $10.20 divided by 2, I get 5.1 miles. That's my standard deviation of my new distribution. Now, here's what's important about that, is I took a distribution of money, okay? A distribution of the amount of fares that he had on his receipts, okay, at the end of the month. He gave me a mean and a standard deviation and no more. I didn't have any data to work from. He could have had 2,000 rides that month, okay? But I don't have to work with all that data. I can work with just the mean and the standard deviation, and I can transform that into the miles that he rode, okay? And I can find the mean number of miles and the standard deviation of the number of miles that he drove with them. Turns out New York City drivers don't really need to go that far on average, but they have a lot of variety, right? Because maybe they need to go to a different borough, okay? And maybe they just need to go down the road. If the businessman standardized all the fares, what would be the shape, center, and spread of this distribution? The shape is skewed right. Shape doesn't change from linear transformations. Okay, that's what we determined on all these other distributions here. Okay, that the general shape is not changing from skew to symmetric, or symmetric to belt-shaped, or I don't know. Okay, the center is 0 because center is subtracted from center, which is 0, and then divided by standard deviation, which is still 0. Spread is $1 because sigma is not affected by addition or subtraction, so we don't subtract mean from sigma. Sigma is divided by sigma, and sigma divided by sigma equals 1. Okay, and that's as far as we got in previous years. All right, thank you for joining.